Dear students, I am happy that to discuss about this second unit in your syllabus, that is designing experiments. Okay, I will discuss about that afterwards. Before that, let me discuss about the analysis of variance. What is ANOVA? Analysis of variance we say. So in this unit we are going to discuss about three types of ANOVA. The first one is one way ANOVA, and second one, as you see here, we get two way ANOVA. Okay, then third one we talk about three way ANOVA. So there are three types of ANOVA we are going to discuss here. The first one is about one way ANOVA. Okay, and that consists of this particular table. Okay, this particular table, one way ANOVA. In your university question, they may ask to describe about one way ANOVA for 8-mark questions or 2-mark questions. You must write this fully, and that is the description of one way ANOVA. Okay, so this one way ANOVA consists of 1, 2, 3, 4, 5, 6 columns. The first one is source of variance. Source of variance means in which way we are analyzing the variance, whether we analyzing column wise or whether we are analyzing between row wise, or we are analyzing between what can I say, treatments we say. So on the basis of that we are calculating the source of variance. Okay, so source of variance, here we are going to find out the ANOVA with respect to column wise. That's why we are writing here. So error term also very important, because to calculate the variance, this error term is very important. Column wise error term we say. Now look at that, sum of squares, that's what you have to understand, sum of squares. Here short form, what is expansion? Sum of squares column wise, sum of square column wise. So that formula is available here, sum of square column wise. That is what this formula, so we will discuss that later. And then here sum of square error, that's what we need to understand, sum of square error. Now coming to the third column, this is the degrees of freedom. For SSC, the degrees of freedom is C minus 1, where C is the number of columns in the given problem. In the given problem consists of columns and rows. How many columns are there? That is C, so C minus 1. And here is N minus C. What is N? Total number of observations. C, the number of columns in the given problem. So we will discuss this when the problems we do. Okay, at the time of the problem solving, I will explain you this, what is N and what is C, everything. Now coming to the fourth column, that we are calculating means of squares. So for SSC, the mean square column is given by this SSC divided by this degrees of freedom. This is degrees of freedom, and that way we can get the MSC, mean square column. So mean square column is nothing but SSC divided by C minus 1. That you will get MSC. Now next one is about MSE. MSE, mean square error. Mean square error. Mean square error is nothing but square what is that? Sum of the square error. Sum of the square error divided by the degrees of freedom. Okay, so sum of square error divided by degrees of freedom of SSC. SSC. That's what we have here. Now coming to the fifth column, this is we find out the calculated value of F. Calculated value of F for what? Column wise. So that is nothing but this MSC. In this place I do want to say one very important point. MSC, this will give you a number, and this MSC, this will give you a number. So we are comparing this number with this number. If this number is greater than this number, if this number calculated value is greater than this number, then FC is calculated as this MSC in the numerator and MSE, that is this, in the denominator, that is equals FC. So FC is nothing but MSC divided by MSE if MSC is greater than MSE, and this value is greater than this value, and then this is the calculated value of F. Okay, MSE divided MSE will be a number, and that number is calculated value of F. Okay, now in some cases this MSE may be greater than MSC. MSE is greater than MSC. MSE is greater than MSC. So in that particular case, this value, that is in the numerator MSC divided by in the denominator MSC, and that number is called a calculated value of F. Okay, so this way we can calculate the calculated value of F. Calculated value of F. Now what about F of t? Tabulated value of F. Fisher's statistical value. What is the tabular value here? Now look at that. This one, if MSE less than MSE comes, then the denominator, where is that? MSC, its degrees of freedom we have to write first inside the bracket. Look at that. The numerator, its degrees of freedom we have to write first inside the bracket, and then MSE in the denominator. MSE in the denominator. MSE, what's its degrees of freedom? N minus C. Degrees of freedom is N minus C. That you have to write in the second place. Second place. Sometimes this may take place when MSE is greater than MSC. When MSE is greater than MSC. When MSC is greater than MSC, then F of C is nothing but MSE divided by MSC. MSE divided by MSC. So in that particular case, what is the tabular value? What is the tabular value? That's what we have to understand. In that particular case, MSC, its degrees of freedom is N minus C. N minus C. And denominator MSC. MSC, its degrees of freedom is C minus 1. C minus 1. C minus 1. So for this, you have to see the F table with the given significance of level of significance, and this is in the horizontal direction, this is in the vertical direction, and the intersection of the horizontal value, this value, and vertical value will give you the table value for F. So this is a way we can get the calculated value and tabular value. Then we can compare As dear students, in the last session we discussed about this one-way ANOVA. ANOVA means analysis of variance. That's what we were discussing about that, and the elements of this table also we discussed. In today's discussion I am going to take two-way ANOVA. This is what we say, two-way ANOVA. So as we discussed in the one-way ANOVA, this also can be discussed on the basis of the one-way ANOVA, and that is just expansion of one-way ANOVA is two-way ANOVA, analysis of variance. As we studied last case, here also 1, 2, 3, 4, 5, 6 columns are there. The first column talks about the sources of variance. The column and row, these are the sources. So between the column, any association is there. Between the row, any association is there. Between the column, association or other terminology, we call it as homogeneity. Homogeneity exists between the column elements or column variables. Similarly, homogeneity exists between the rows. Okay, so these two we are going to discuss here at a time. Okay, at a time we're going to find out whether there is a homogeneity between the columns, and as well as is there any homogeneity between the rows. So two at a time. In the previous case, you look at this table, we discuss only the homogeneity between the columns. Between the columns, is there any homogeneity? That's what we are interested. But if you look at this particular two-way ANOVA table, we are discussing both the homogeneity between the columns as well as the homogeneity between the row. So this will be clear when we do the problem. At the time I will explain a little bigger than what we discussed now. Second column, sum of squares, and in that case between column we say sum of square column wise. We say sum of square column wise. There is a formula. Now look at that. This is the formula already we have discussed. Okay, summation x1 squared by n1 plus summation x2 squared by n2 plus dot 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 summation xn squared by n minus t squared by n. Okay, so that's the way we can calculate this. Then between the rows, what we calculate or the sum of square row wise. Sum of square row wise we are going to find, and the last elements in this column is sum of square error. Sum of square error, that's what the last elements in the second column. Coming to the third column, degrees of freedom. Degrees of freedom. Okay, so for SSC the degrees of freedom is c minus 1, or between the columns the degrees of freedom is c minus 1 when c is number of columns. Degrees of freedom, to find the homogeneity between the row is r minus 1. The degrees of freedom for row is r minus 1, and last one is n minus c. N means number of observations. When we do the problems I will discuss, and here c implies the number of columns in the given problem. Okay, and then mean square, means of squares, mean of squares, means of squares you can say. This is nothing but mean square column wise. We say mean square column wise, mean square column wise. The formula is this SSC, sum of squares column wise divided by corresponding degrees of freedom C minus 1. Similarly, mean square row wise, this is column wise, this is row wise. The formula is SSR, sum of square row wise divided by R minus 1, where row means number of rows in the given problem. Now the last one is mean square error. We say mean square error. That is nothing but sum of square error, that is sum of square error divided by n minus c, the degrees of freedom. Okay. So this way we can calculate MSC, mean square column wise, MSR, mean square row wise, and MSC, mean square error. The next column is to find out FC. That's what we have to find out. I already told you that we have to take MSC and MSE. These two we have to take. Okay. There are two possibilities. I mean, this value may be greater, this value may be lesser. So in that particular case, we have to write MSC in the numerator and MSE in the denominator when MSC is greater than MSE. Suppose this is greater, this is lesser, then MSE will come up and MSC will come down. That is a value, that value is FC. Okay. So in the same way, MSR is greater than MSC. Suppose that MSR value, we are going to get value here, and that value is greater than this value. Then we are writing this in the numerator, MSR divided by the small number in the denominator. If this is the case, MSR is greater than MSC. Other choice is also there. MSC may be greater than MSR. In that case, you have to write MSC divided by MSR. That you have to write. Okay. And here MSC divided MSC. Okay. That's what we have to understand. But this is not needed for us. Okay. We are not going to calculate this. This only we are calculating. That's why we say it is two-way ANOVA. Whether there is a homogeneity between the columns as well as whether there is a homogeneity between the rows. That's what we have to discuss here. Okay. So I think this is not necessary for us. This is not necessary. Okay. This is not necessary. Now, how to find out table value of F? Table value of F, how to find out? As I told you already, F of t inside the bracket, suppose this comes in the numerator and this comes in the denominator. In the first place, the numerator degrees of freedom we have to write here. And this is less value, that is in the denominator. Therefore, its degrees of freedom we have to write here n minus c. Then going to the table, okay, going to the table, we can find out the FT table. Similarly, row wise, if MSR is greater than MSE, that is, this is numerator, this is denominator. In the first place, this is numerator, that degrees of freedom we have to write here, and this degrees of freedom we have to write here, n minus c. MSc degrees of freedom is this, that we are writing here. Okay. Suppose this is greater, this is lesser, then this n minus c we have to write first, then r minus 1 we have to write here. Okay. So this is the way we can calculate the table of value for column wise as well as row wise. So we are analyzing column wise and row wise at a time. That's why the name two-way ANOVA. Two-way ANOVA. So good luck. The next session we will discuss about three-way ANOVA. Thank you. Okay, so students, in this session we are going to discuss about three-way ANOVA for Latin square design. Okay, three-way ANOVA, what is that? Now look at the table here. This gives you about three-way ANOVA. Now, as we know, source of variance is between columns, between rows, and between treatments. So there are three variables we are going to discuss here: whether there is a homogeneity between the columns, or whether there is a homogeneity between the rows, or there is a homogeneity between the treatments. That's what we are interested. For that, this three-way ANOVA table may be useful for us. So in the 8-mark question they may ask this. So this table you have to remember in order to get the mark in the examination. As we do SSC, it is sum of squares column wise, is degrees of freedom, not degrees of freedom, is k minus 1. And how to find out MSE? This is nothing but SSC divided by k minus 1. What is this k? This k is the number of treatments. When the problem comes, I will explain you what is k. So how to calculate MSE? It is nothing but SSC divided by k minus 1. And then FC, if MSE is greater than MSE, we are calculating here. You are comparing this and this. Okay, you are comparing this and this. In that particular case, suppose this is greater, this is lesser, we usually write the greater value in the numerator and smaller value in the denominator. Okay, as greater than 1, this fraction should be greater than 1, and this would be the calculated value of f. Now coming to the second one, between rows, SSR, sum of square row wise, is degrees of freedom is k minus 1. And how we are calculating MSR? SSR divided by k minus 1. And this also some values will come there. And how we are calculating the calculated value of row wise? As we do, MSR is a number, MSE is a number. We have to compare them. Which one comes up is the greater value. If the greater value, we have to write at the top, and the lesser value we have to write in the denominator. Sometimes this may be greater, this may be lesser. In that case, you have to write MSE by MSR. And then for treatment also, the third analysis here is on treatment. So that we call it as SSK, and here k minus 1 is again the degrees of freedom. How we are calculating MSK? We are calculating this SSK divided by k minus 1. That way MSK we can calculate. Here also we are comparing MSK with the MSE. If MSK is greater, MSE is lesser, we are writing like this, and the calculated value of treatment we are writing in this way. You will get one number that is called the calculated value of treatment. The last one is about residual, or we say error terms, sum of errors. That degrees of freedom here is k minus 1 into k minus 2. K minus 1 into k minus 2, the degrees of freedom for residual. How to calculate MSE? SSE divided by this SSE divided by this degrees of freedom k minus 1 to k minus 2. So by comparing MSE and MSE, we can get a calculated value. How? The greater value you have to put at the top, and smaller value of this element and the MSE elements, put down, and that will give you the calculated value of FC. Now a tabular value, as I already told you, that if MSE is coming up and MSE is coming down, the corresponding value is k minus 1, and here is k minus 1, k minus 2. That way we have to write. Similarly, F4, if MSR is greater than MSE, then we have to find the tabular value of F by taking the numerator as k minus 1 and the denominator as k minus 1, k minus 2. The treatment also, if MSK is greater than MSE, we are writing like this. Then we have to see the F table such that the numerator is k minus 1 and the denominator side we have to take k minus 1, k minus 2. That way we have to take the table value of FT. So that is the way we can calculate, and we will get the calculated value, table value. We can get the calculated row wise, table value row wise. We can get calculated value for treatment wise and the table value for treatment wise. From them comparison, we can take the decision on the three homogeneity through columns, through rows, and through treatments. And this is how we are discussing a three-way analysis, and this is used for Latin square problem. Latin square problem, this type of analysis is used. So lattice type of problem means it will be given like this, okay, where the design consists of row columns. Not only that, some blocks also will be given like this. Okay, this is the block, this is the cultivation, like that. So that we will discuss by taking one problem and discuss that in another class. So thank you very much for showing interest on my discussion on three-way analysis. Thank you.